Good afternoon. I'm Merriam. My co-speaker is Sherry Wood, my wife. She doesn't know anything about C++, but I could get her in here by getting her in here to see my talk by making her a speaker. But she was an English professor, so if you want to know what pluperfect means, she's the person to ask. The only thing I know about it is English doesn't have it. So the talk is Meandering Through C+, Creating Ranges 2. I'm very interested to hear the keynote about the advent of code, because in 22 I started with the advent of code, reading Simon Toth's articles, because every day he was solving it and writing an article about it on medium.com. When I got home from the cruise I was on, I solved 3 days worth of the puzzles and then went back and looked at his code. And it was all ranges library and pipelines and so forth. And that led to last year's talk here in CppNorth. So this year Advent of Code started, and I said, I'm going to do everything with ranges. I really want to dig in and learn how to use it. And the only way to learn how to use it is by doing it. And I beat my head against the wall a number of times with that. So as I was working with it, though, one of the things that kept nagging at me is I wanted to try using ranges too, but I was on GCC 13.2 on Linux or Clang, and neither of them had a version of ranges 2. Microsoft had, I believe, a limited version of ranges 2 at that time, and it was going to be April until it came available. So once I got done playing with AOC, I could only do about 10 days worth of it, and I get tired. I said, well, what's the problem with ranges 2? Why is it so difficult that they didn't get it done sooner? Didn't seem like it should be that complicated. So I dug into it, and that's what motivated this talk, is the experience of going through that process. And maybe not so much for the people in this room, but when people are looking at this at YouTube, the really new developers, I hope, see that how this graybeard went through the process. And whatever process they follow, if it's similar, that's a good process. At least it's a workable process, and you'll get there. So I started with C++. Oop, wrong button. There we go. Who doesn't recognize this? You don't count. Okay, so real youngsters here. Of course, for me, anybody under 50 is a youngster. This is Borland Turbo C++ in 1990. So I learned C++, reading manuals for this, for Borland C++, at Waikiki, sitting at the bar at the swimming pool. I was there with my ex-wife. I was the spouse for a conference that she was attending. So that's where I learned C++. Now, I've got a fair amount of experience here. 1968, first program in Fortran 4. That's when the university centers were trying to get people to use it. I actually went to a 6-week seminar, and they taught me how to do Fortran and use the computer system. A bunch of other languages. I did teach Introduction to C++ at University of Houston Clear Lake. I've used C++ in some robotic competitions. 3 of them for NASA, one where I actually had to build a robot that went and searched a park area, which was a sample and return project, which is what the mission this year, 2024, is supposed to do. I think it's been canceled, or it's not going up, to pick up samples that the current rover is scattering around the Mars landscape. And then another one was 2 simulations, again, another one on Mars with a humanoid robot that had to go fix some things after a storm messed things up. And then one on the moon where it was mining equipment, where they were gathering stuff for minerals and oxygen and everything else. And NIST, National Institute of Science and Technology, runs a competition every year. I think they may have stopped, which was manufacturing, basically collecting parts, putting them in a shipping box and sending them out, and you had to detect defective parts and flip them over and move them around. I've written about C++ in various places, 90s in the magazines, Hackaday.com, the late teens of 2000. And I tried to address C++ for embedded systems, of course focusing on Arduino and Raspberry Pi, but to convince, in general, embedded developers that you can use C++ and move away from C and get the advantages that C++ had, and demonstrated that no, it doesn't cost you a lot of money to use time or effort to use classes. It's just as efficient as C in general. And more recently, some work on medium.com, whatever strikes my fancy to write about C++, a little bit on LinkedIn recently. So what is ranges to? And this is from the proposal, Conversions from Ranges to Containers. And I usually don't directly read from the slides, but I'm going to read this one. Function that can materialize any range as a container, including non-standard containers and recursive containers. Everybody understand that? It's about clear as mud. Okay, materialize, copy. Move it from the range to the container. Non-standard containers, things that aren't in the STD, not in the standard template library. So like Boost library, if it conforms to the container type definition. Recursive containers, containers containing containers. A vector of lists, of sublists, of sets, or something like that. Be able to handle all that capability. Why do we want ranges to? What's the big deal about it? Well, it simplifies code, just in general, but it also has the power to evaluate a pipeline. Now, pipelines are lazy evaluation. When you create a pipeline, you assign it to a variable, you've just created a pseudo function, and it doesn't do anything until you start asking it for information. Typically, you'd use a range for each, fold left, some routine that actually asks it every time for the data that it can process. So don't bother terribly looking at the top stuff here. Just see that there's a bunch of lines of code, and we simplify it when we get to ranges to, like here, we can convert a list to a vector in a pipeline by simply invoking ranges to at the end instead of going the two lines of code above. Or we can call ranges to directly, invoke it as a function, and create the vector. Here we got a little bit more complex setup information with IOTA generating numbers and so forth, and we copy things. We can just put our IOTA as the first part of our pipeline and invoke ranges to create a vector. Here we start with a map, and we want to convert it to a vector, reserve the map size, move it, and so forth. Far simpler to say, just get the map, invoke ranges to, and we wind up with the vector. Now, this is from the proposal, and they should have something on that to, which is the vector, that the container that they want to use. I would have fixed that if I had noticed it, but I just noticed it yesterday. Implementation requirements. Okay, the proposal goes through a list of things that ranges to is supposed to accomplish. So we need some data. Just fake out a little string there in a string view. We want to create a container with elements of data. That is our string vector, string view here. So we can say we've got to with a standard vector of character, and that'll create A here becomes a vector of characters. We can do conversions. That is, we convert our characters to long. And in fact, ranges to in the standard is in a section called conversions. We also want to be able to deduce the type of the elements that are going to be in vector as the same type that's in the range, in this case characters. We want to convert sequence containers, that is vectors and lists and so forth, to associative ones. So C was a vector from the last page. We're converting it to a set D. We want to go backwards. We want to go from an associative to a sequence. So here we're creating a list from a set. We want to be able to convert nested ranges. This is the containers containing containers. Here we've got a list consisting of 3 forward lists of integers. We can spell it out, standard vector to standard vector of integers. Or we can say standard vector to standard dec of double. So we can do a conversion at the same time. As we'll see later on, you can also do a deducing version of this where you don't have to specify what your containers are, or you specify the outermost container without having to specify the data type. We want to work in pipelines. So here we take 3 characters and we want to put it in a vector, and that results in F. Also do the data conversion. So again, here we're converting characters to long. Okay, I'm going to show you a bunch of C++ code. It's substandard. I'm limited on screen space here. So I'll leave out things like const, no except, whatever I have to do to get everything down in the number of columns and lines I've got on the screen here. And some people call this sideware. I call it conceptware, because really what I want to show you is concepts. It's not so much that you take this code and work with it, but you look at the code and say, oh, that's how he did that. I can do that too over someplace else. Or this is how part of this code works. All this code does work with GCC 13.2 and 14.0, and with Clang 18.1, compiled under C++ 23. I'm pretty sure it'll compile under C++ 20, but it's been a little while since I actually did that. I haven't done it in the last few weeks after the latest changes that I've made. Some conventions that we're going to see. We do a lot of templates here. So T is just the element data type that we're specifying, like an integer. Con by itself is a container without the element type specified. Con T is a container with the type, vector integer. And RNG, range, means our range that we're going to be working with. And in every case here, it's actually an input range. We use some namespaces to simplify the code, range and views, and again, our data. And you'll see this contest, which is what I use to test the routines. It's got a text which tells me what the test is particularly taking place, and it calls convert with const and the source. And I use format print line because it automatically prints out ranges, which the one in the standard does not yet do. There's another version of this. This is the one with the specified element type. There's another version of this with the deduced element type, but it's basically the same code. So what's the signature of convert with the element type that we want to work with? And we want to do convert vector of integers. So it's a template with the type name cont, an input range, and the function call a convert with const. So we've got an input range, and we've got a container with the element specified. Now my first pass was to use copy. We just create our const as our destination, and we use the constructor that takes the size element to allocate how many elements we're going to have in there based on the size of the source input, and we do a copy to destination begin, and everything works fine. And indeed it does work for vector, and it does work for forward list and the other sequence containers. What it does not work for is set, because set has no size constructor. Kind of makes sense. How do you know how big a set is going to be when you got, duplicate items in its source? It also doesn't work for stack, because stack doesn't have a begin member. In particular, the size constructor is missing from set, multiset, unordered set, unordered multiset, and we don't have begin members for stack queue and priority queue. So I said, okay, we'll brute force it with a range 4. And if you look at CPP reference at the bottom of the containers page, there's this big table which is all the containers and all the member functions for the containers and which container has that specific member function. And I went through that list trying to find what would work for all of these things. And my first pass through, I wound up with like 3 different functions that I had to use to make this range 4 work. And then finally I dug through a little bit more and I said, oh, all of these have in place. And you'll hear me repeat this. I kept digging through things and looking for simpler solutions, better solutions. So this is the one I came up with. So we create our container and we place all the elements from source into the container and return it. It works for set, it works for stack, it works for queue. It doesn't work for vector or any of the sequence containers, because the sequence containers have it in place, but it requires a position and an item. So can't use it. So at this point I'm thinking, well, okay, I've got to have the copy version and I've got to have the range 4 versions. So how do we do that? Well, here's our first meander off the main path that I'm working on here. We get into concepts so that we can tell the compiler how to differentiate between these 2 functions that have the same signature. And the first step is a requires clause. A requires clause has to yield a Boolean expression. It specifies constraints on template arguments. In this case, we're saying, in this example, that template T has to have EQ and take T as a template, whatever EQ may be. And that makes, if that's true, then this function is acceptable to the compiler to use for further determination if this is a function that can be used. We can also put it on the function declaration itself. So in this case, the requires EQ goes right after the parentheses on the function definition. And now, just to keep things confusing or interesting, whatever your perspective is, we also have requires expressions. Anybody else wondered about the standard committee with requires in 2 places here? I don't know. Again, a constant Boolean expression it must result in. You can use it with if constexpr as part of its test. And you can use it on a requires clause. And this is where it gets interesting. So we have our template with the type name T, and you say requires, that's the clause, and then you get the expression requires. Again, T has to have equal to make this function acceptable for the compiler to determine whether to select this or some other version of the function f. So one approach, as I showed last slide, is use if constexpr. constexpr requires, and this is just a requires expression, requires, DST resize. Resize is if the constructor has the size constructor, then it also has a resize function. So this tests for that, but I didn't use the size constructor anyway. So we resize it and do it our copy. Else, we use the range for and do the in place. And return the whole thing at the end. Now, a little bit of a soapbox. I come from structured programming background. A lot of it in the 70s and 80s from structured programming. You enter at the top, you leave at the bottom. You don't do any intermediate returns. That's dangerous because you don't know then which return is returning. If you put it at the end, you know you're getting the return there. You can work backwards from there fairly easily. If you want to do some conditional tests up front to make sure constraints are satisfied, that's different. But once you get into the body of the code, enter at the top, leave at the bottom. Okay, off the soapbox. So here's how we set up the differentiation. Here's our copy version. It requires, and I put it in parentheses, resize, and that determines whether this function can be called, can be used. I'll put the parentheses around it because you can have multiple requires expressions in a requires clause. So if you have multiple conditions you want to test for, you can do requires, and it have to appear in a parentheses then. So here's our other version of it, and it's just the straight version we had previously. Now the compiler will select the most specific version of the function, the one that constrains things the most. So if it's got the resize, it'll take that one. Otherwise, it comes to the second one for in place in the range 4. Here I'm just putting out our copy version as we're working with it right now because I want to show you concept and how to apply it. If you had a whole bunch more of these convert functions, then you might want to turn to concepts because it does simplify the coding a little bit. So we require a concept, which is a template, concept, and placeable. And it says it requires E to have an in place member. Then our second function, we can specify in placeable as the type for the template. Parameter const in our range, and that's acceptable for that. So you've got, the compiler is going to look at this and either I got this one or I got that one, and it can decide at that point specifically which one it wants rather than defaulting to the second one. So if you ran into some other strange situation, perhaps with a non-standard container, a container that's not in the standard, this might say, oh, this one doesn't have all the things we need for either of those cases. So as I say, I keep looking around and I keep poking at things, and I'm reading a blog that says initialization is more efficient than copy, because with copy you've got to construct your container, perhaps size it, and then call your copy. Whereas initialization, it all happens in one step, and the compiler can do that more efficiently. So I said, I wonder if I can do initialization instead of copy. This compiles nicely. And we're using the ranges version standard functions, not member functions, of begin and end to handle what's called first and sentinel. Another meander. What's a range? Range is an iterable sequence. Well, we kind of think of that as we can step through it forward or backward, maybe even jumping around it. What it really more means is there are iterators that work on this range. And we're familiar with ranges really because they're out of the standard template library that we've worked with since the 90s. If you've got a sequence of first and last, which we know is begin and end, then you've got a standard container. Now the bracket, square bracket in front of first means first is included in the range. The parentheses after last means last is not included in the range. And we're familiar with that too because we know that the end function, the member function, is beyond the range. We're done when we hit the end function. And that's standard, containers, vector, list, array. But now we've got a sequence of first and size. So we know where we begin, we know how big it is, but we don't really know where the end is. A stack. Stack we know the size of, we know where it begins, but we don't know where the end is. Sequence of first and predicate. That is something that we can test, say, oh, this is the end. Again, we're used to that. C character arrays, end with /0 at the end of them. But another case is streams. The end of file predicate when you're reading a stream. Then you've got a sequence of first, and I don't know when it's going to end. And these are called generators. IOTA is one of the generators, random number generators, so forth. So I see IOTA. I said, IOTA generates a sequence of numbers. You can tell it where to start, or it starts with 1 and gives you, every time you call it, it gets the next integer. And I wonder where in the world did they get IOTA from instead of saying, number sequence. Well, it seems long ago that IBM wanted to talk about programming on the blackboards and whiteboards. And they devised this notation which was all character-based. It wasn't, a language like of it today, unless you're working with functional programs. IOTA was the Greek character that represented a sequence of numbers. So we got IOTA from that. And the language actually became a programming language, and that was its name, a programming language, APL. It was a write-only language. Come back 2 days after you wrote a sequence in APL, and you didn't know what it was doing. If you want to hear something related to APL, come to Connor's talk later in the conference. He will probably even mention APL because it's kind of the grandfather of all these functional programming languages today. I mentioned this last year. I think you let out a yelp when I mentioned it. So in general, we have a first and a sentinel. And sentinel covers all of these different cases. So when you're talking about ranges, a range is defined by the fact that it has a first and a sentinel. So we have our begin and end as the source. One of the things that using begin, the range begin and end, or constant begin and constant end, is they work with all the different container types. So it works fine with the sequence containers, works fine with the associative container, vector and set. We can put a pipeline in as the input to it, and it works. What it doesn't do is nested types or these containers of containers situation. Now here I use chunk, and chunk, the view chunk takes 2 characters out of our input. So you wind up with a vector consisting of some elements that have 2 characters in them. And I played around with here trying to use a 2-character array and that sort of thing. It didn't work. And I finally realized why later on. I'll mention it. Now we want a version that deduces the type. We don't want to have to specify the type. So con has an element type that says type name ... which means it's got a template pack, parameter pack. Think of vector. Vector has two template parameters. It's got its data type and it's got allocate. What was interesting is I had this code working with GCC and I didn't have the dots in there. And it worked. I got Clang on my system and tested it, and Clang said, nope, this doesn't work. I don't know what you're doing here. Clang required the 3 dots. So Clang wanted it. GCC works with it. It accepted it, so it was fine. But I thought it was interesting that GCC didn't require it. So we've got con, which does not have the data type. We're basically saying on that line, con is a variable template. I'm sorry, a template variable. And we'll tell you what it is later. So we get our input range. And then to figure out the type of element, we use range value t to get the data type. And it took me a while to find this. I mean, I knew containers had value type, but I was digging through CPP reference and finally got on the list of all the usings that are available for ranges and said, oh, yeah, range value type, that works. OK, so we have this. And note what it calls. It calls our previous function to do the actual work. Because now we know what the data type is, we can specify it, we can use convert with a specified type. I warrant if we looked at this code in CPP Insights and you actually used it, this piece of code, these lines of code here, would actually not generate any code. The compiler would do all its magic, figuring out all these types, and just call our explicit version. OK, so what works at this point? We can convert our standard character, vector, specifying character. That works fine. We can do our conversion again. We can convert deducing type, do a deduction, so that we get the same data type that's in the range. And wow, nested ranges works. I was afraid I was going to have to get into some form of recursive calls of convert to get these sub-ranges under the main range. But it works. Why? Because it figures out the data type of the sub-range. In this case, is exactly that, a sub-range of 2 characters. And, hey, is this a great world or something? What? OK. I almost changed the slide to be a little bit less snarky, but here there be dragons. But yeah, there's a little bit of a rough ride coming here. We have to pull some tricks to make this work. It's understandable once you understand. You'll understand it once I explain it. But getting there just takes a little bit of patience. What we've got to create to work with a pipeline is a range adapter. If you look at the current library, you've got like take and take view. Take view is the underlying function. Take is a view which, if it needs to, invokes take view. And there's some criteria where take does not need to call take view. Like if it will detect if there's an empty range coming in, I don't need to call take view. And there's some other conditions where it doesn't even have to call take, which saves greatly because you don't go through all the construction of creating the underlying take view and other expansion of templates, so it will decrease your compile time. Note, there's no argument. We're not passing anything in there. So it's picking it up, much as would do with, like say, creating an output stream function. The OStream reference is the first parameter, but the chevron operator slips in the output stream that you're working with, and all we have to pass in is the data we want the stream to generate. Same thing here. We don't have any data we have to pass in. So we have to create, so our function without arguments, again, we're starting here in reverse order this time with the deducing version of it. And it's going to return an instance of the structure convert with a capital C, specialized from container con. So we get our container, pass it in con, tell convert your structure with con, do your thing, and we create an instance of it. That's what the two braces at the end of the line mean. How does this work? Well, first of all, we put this in namespace detail because it's implementation details. So we don't want the users getting into this stuff. We again have our template type name for con, so that we're telling it this is going to have some type template parameters. And we create a structure convert, and then we inherit from range adapter closure, and we pass our own self, our structure with our data type template from the template to range adapter closure. This is the curiously recurring template pattern. We'll talk about that more in just a minute. Next meander. We also have a pipe call operator, which turns around and calls the convert functions that we just wrote. So this is the two parentheses you see at the end of convert. Okay, curiously recurring template pattern. James Copland gave it this name in the 90s. It's an idiom, not a design pattern, as we think of them today. They were kind of contemporary things coming out where he talked about CRTP, and the Gang of Four was publishing their book on design patterns. It's called curiously recurring because it was actually seen in multiple languages. Smalltalk, at least. I don't know if Java was out at that point and could use it. No, they couldn't because they didn't have templates at that point. But it was seen in different places, and that's why he thought it was curiously recurring. And basically, as we've seen, the derived class is passed as a template argument to the base class. If you want a little bit more in depth, it's just a few more slides than this. My talk at CppCon on non-virtual polymorphism mentions this at the end of it, because this is a form of static or compile time polymorphism. So effectively, we have our struct range adapter closure, expecting a template parameter called derived, and our convert inherits from range adapter closure, passing it itself and its type. Yeah. So next step is to get the explicit version of it. And I gave it a different name, convert typed. It does the same thing. Call range adapter closure, pass in itself, and it's the data type that it's supposed to represent. We got the call operator, and in this case, we have a version of convert that calls convert typed. And convert typed would be in detail. In namespace detail, I just left that off. Now, I hadn't really studied, say, ranges v3. I had looked at it to just kind of skim through it. And eventually I did look at the GCC version of it. And one of the things that puzzled me when I was looking at these before I got to this step was why they were having what appeared to be basically the same things appearing twice. And I finally realized, oh yeah, because you have to do the different type for explicit and deduced type flavors. So next thing, I had to test these things. So remember, pipelines are evaluated when they're invoked. They don't, they get assigned to a variable, and then you've got to do something to make that variable process the data. You can't make a list of them and store them in containers because they're all a different type. Their data types are all different. But standard tuple will handle multiple data types. Again, I touched on this in the CppCon talk. So if we want to test pipelines, we can create a std tuple called pipes test and put in our different pipelines we want to test. And then we're going to call test pipes, a function we'll see in a minute, with this pipes to test and the data. Note here that for join and enumerate on split, I added common because join and enumerate, depending on what precedes them, may not have a begin and end. And common gives them the begin and end. There may be a trick I could do in my convert code to avoid this, but I was at the point where I said, okay, this is good enough. I'm not going to mess with it. I can use ranges too because it's coming out soon enough. So test a pipe is a lambda, and all it does is it invokes the pipeline using our convert function with vector, and it just outputs. That's all the constexpr here does. Determines whether it's a nested range, in which case the format print line's got to have a format join to make it look pretty. Otherwise, if it's not, we just format print line itself. To work with a tuple like this, we have to use apply. And again, talked about this in my CppCon talk. I don't want to get it. But std apply creates a call to test a pipe for each pipeline in our list of pipes, the one that's in the tuple, all of them, the items that are in the tuple. And convert pipes expands all these template parameter lists, all these dots get expanded to contain our data or a single pipeline. And what's interesting is I have all these things in different modules, and when I compile and it compiles this specific code, it takes longer to compile because it's doing all this expansion out of the std apply. Interesting side note. Std array is what they call tuple-like. You can use apply with std array, which means it's loop unrolling. So if you're processing in a loop, one of the techniques for optimization is to call each of the items separately instead of iterating through them. It's a little bit more efficient. Std applied will do that for you automatically. So that's my meander through writing ranges 2. Hope you enjoyed Toronto and CppNorth 2024. Thank you. Yeah.
Very good talk. Thank you very much. I think the issue with ranges comment that you had might have to do with your move to initialization of the containers through an initializer list. I think initializer lists don't really support sentinels as well, and that may be why comment is needed.
Yeah. Yeah. As I said to start with, it was the process I wanted to explain here as much as anything. And some of the issues about C++ in general. And I'm sure there's other ways of doing this. I haven't studied the library code because it is so difficult to understand the library code, no matter what version of it is, who it's from. I haven't dug into it a lot, and I just said, okay, I got what I want. I'm going to walk away from it now and, take a breather. Again, thank you.